Choi. I'm an assistant professor in civil and environmental engineering at FEMA FSU College of Engineering. I'm also the director of the NSF-sponsored Sustainable Material Management Reconnaissance Events Organizations, or SUMMEER. Before we get started, and introduce today's speaker, I would like to take some moment to briefly introduce the SUMMEER. So as you may know, NSF has sponsored several reconnaissance organizations, such as the GEAR and NEAR and STEER and OSHERS. So actually, the SUMMEER is one of the newest NSF-sponsored reconnaissance organizations. And like the other ER organizations and also the natural hazard research facilities sponsored by the NSF, SUMMEER also has the missions for training to train the researchers and coordinated the reconnaissance teams to collect the post-disaster data important for sustainable disaster research. Just in case, I'm pretty sure many of you have already joined the SUMMEER, but just in case if you're not joined, you have not joined the SUMMEER, please please join us by scanning the QR code that you can see from this presentation slide, or you can actually visit our SUMMEER website to submit your registration form. Just also before we get started, I also would like to let you know that this webinar is video recorded and then will be shared through the SUMMEER YouTube channel later. So if you go to the for those who are wondering what kind of training videos are available, please go to our website and then you can find the link to our SUMMEER YouTube channels as well. And also, as the last note, for today's training webinar, you are not allowed to unmute yourself. So just in case when you have questions, please use the chat. And then either the speakers or the host, we're going to communicate your questions to the speakers so that speakers can answer any questions. And also, as we previously communicated with you through the email, today's webinar is about how we can use the discrete event simulation software, which is called the JSTrobe. So for those who have not installed and downloaded and installed this simulation tool in your computer, please download this application following the instructions that is available in the chat. Okay, finally, I would like to introduce today's speakers, Dr. Joseph Lewis. Dr. Lewis is a faculty member in the School of Civil and Construction Engineering at Oregon State University. Dr. Lewis' research interests lie at the intersections of the simulation, visualization, and automation of the construction operations. And also he has taught a lot of courses in the heavy equipment operation and project risk management. Especially in his research, he has developed various operation analysis, and he has used a lot of the various operations analysis and visualization methods, including the simulation software. Especially, he's the developer of the JSTrobe that today's presentation is about, and he is going to demonstrate to you how to use the JSTrobe to better understand the debris removal operations. Please join me welcoming today's speaker, Dr. Lewis.
Thank you so much, Juyang. Hope you all can hear me okay. So I'm just going to share my screen. All right, you should be able to see that now. So again, good afternoon, everyone. So it's still afternoon here. So my name is Joseph Lewis. I'm an assistant professor in the School of Civil and Construction Engineering at Oregon State University. And I'd really like to thank you all for being here for my presentation. It's a holiday, it's Veterans Day, so thank you to all the veterans. And also thank you especially to Juyang and his team at SUMMEER for giving me this opportunity to talk about this tool that I've been using and working on, and especially as it applies to debris analysis operations. So we'll be talking about discrete event simulation and how that can be applied to debris management operations. So the way this presentation is structured is, I'll spend the first few slides talking about the importance of debris management operations, especially within the context of SUMMEER, and thinking about ways in which we can incentivize the sustainable disposal of debris. And then we'll kind of switch tracks a little bit, and we'll build out a small model in this JSTrobe software. After that, we'll spend a few slides just talking about how this small piece of operations analysis can connect to the larger issues of debris forecasting and route analysis and geospatial analysis. All of these tools, which have been are pretty well integrated into the practice of emergency management for disasters. All right, so let's get started. So you've probably heard this number, right? Let's start with why focus on debris itself. You've probably heard this number about the 27%. That comes from FEMA, and they've estimated that debris removal accounts for about 27% of recovery costs, which is an extremely huge amount. And debris removal is also essential for both phases of the recovery operation, which is, response and recovery. And of course, by response, we mean the immediate reaction to the disaster, where we try to clear routes for emergency personnel and for evacuees by moving debris out of clogged roadways. And recovery refers to the long-term disposal of debris, right? And debris is a complex problem just because of the variety of debris types that are generated after a disaster, and the variety of treatment options that are available for each of these different types, right? So if you think about it, there's a lot of decision points that need to be made just about the operation of disposing of debris. So the larger goal here is, by incorporating sustainable management practices into our debris management planning, we can hopefully shorten the recovery times and improve resilience. So that's the really big picture. Just to give you another view of the scale of the problem. So this is just a picture and some facts from the 2011 Tohoku earthquake in Japan, right? So in the Miyagi prefecture, they generated about 25 million tons of debris just after this one single event, which is equivalent to about 100 years worth of solid waste or trash generated in just one day. So you can imagine the logistical challenge and the huge task that it is for officials to manage all this debris. I did some little back of the envelope calculations myself and did it from my state of Oregon. And here we are worried, and we're planning for the big Cascadia event, and we are estimated to see about 10 million tons of debris, which is about 13 years worth of trash. But again, that's in one day. And that's also going to be mostly concentrated here in the coastal regions. So these regions are particularly vulnerable to being islanded and being cut off after disasters and sustaining huge amounts of damage. So it's very important that we try to help with the planning for how we can deal with the debris that's going to be generated. So I want to spend a little bit of a slide talking about why we need sustainable management of debris. As you can see from these headlines here, you can see that disaster debris, it's not just bad that the disaster has happened and communities are struggling to find their feet, but the way we manage debris has some longer term implications. It is depleting the space available at landfills for solid waste management. It's pushing that to the brink. And not only that, as you might know, landfills are one of the biggest contributors also to global warming because it generates a lot of methane gas, with all the waste that's in there. Now, some solutions are to try and recycle debris or to use it for energy. So as you can see here, how could we recycle a 14-story office tower by thinking of how we might be able to reuse some of the demolition debris. So what I try to do here is just talk about some of the opportunities that are very obvious to us for recycling debris. Now, the first thing to note is that disasters generate heterogeneous streams of debris, right? So we have vegetative debris, we can have construction and demolition debris, we can have hazardous waste, cars, vehicles, and so on. So if you're able to separate these out, the vegetative debris can be ground and used as mulch and chips, you can process a lot of the vehicles and larger equipment for scrap and salvage. So that the ultimate aim is that they're not going into these landfills. And a lot of construction and demolition debris can be crushed and used either as aggregate or as backfill. So these are some of the big buckets and big opportunities that we have for recycling. But the problem is that, these methods are not typically used. And that's because these methods are not chosen based on, what's good for the environment or what's good for the community in the long term, but rather what makes sense to do based on operation economics, based on the local logistical site constraints and so on. So that is what kind of motivates us to go and look at the entire process of mapping what are the operations involved with getting rid of debris. So I've kind of mapped out these steps, which I've gotten from the FEMA 325 handbook, which you might be familiar with. That is FEMA's instructional manual on how to deal with the debris that's generated after disaster. So the first step is debris forecasting. And this obviously ideally happens before the disaster occurs. And then you have debris collection, taking them to debris management sites for temporary processing, especially when you don't have landfills available in the near vicinity. And there you can reduce and recycle this debris before it's taken for final disposal, right? But when you look at the tools that are out there that are available that people use, you have some tools, some objective measures, that give you estimates of how much debris is going to be generated and where this debris is going to be and what type of debris you're going to have, using tools like FEMA's HAZARDS or EPA's iWaste tool. These are very extremely useful tools for debris forecasting. But when you look at all of these steps, it's really what happens on the ground in terms of the operations that need to be performed, right? But there's not a whole lot of objective tools that you can use for this operations analysis. What's typically done is contractors use their historical or subjective experience, which is, of course, a very valuable resource to fall back on, but it's not one that's available to everyone to use objectively. And they can use some Excel analysis or quick calculations, which make a lot of assumptions. And the third method here, operation simulation, is what I'd like to talk about today. All right. So let's just think about why we need this operation simulation once again. So we've established that we have heterogeneous streams of debris, and we need to see how these debris are processed through these steps of collection, management sites, and so on, right? What happens is when you really start to look closer at what happens on the ground, you start to get all these decision points for which you need to make decisions. For instance, with debris collection, you got to decide whether you're going to do curbside pickup or whether you're going to have the public come and dump their debris into a collection center after the disaster. If it's curbside pickup, are you going to have the public segregate the debris into piles, or are you going to collect debris and sort it out yourself? So there are all these trade-offs here in terms of how well educated the public is on how to separate debris and what facilities are available for you to separate the debris if they do not do that. With the debris management site, locating these sites it's a matter of great debate, and we need to figure out how we can locate these sites in a manner that provides adequate size and access to the affected areas without impeding other operations and other rebuilding operations that also need to happen, right? So you can imagine that the size of these debris management sites is going to have a huge impact on the logistics of the debris management operation itself. And finally, and next we have our reduction and recycling methods. So we've spoken about some of these. You can have, based on the type of debris, you can either chip, you can incinerate some of this debris, you can try to use it as biofuel, you can grind some of this debris for reuse as backfills, and so on. So, and the alternative is, you just take it for final disposal to a landfill, which again, you have to consider these issues of the landfill capacity, the dump fees, which is a huge factor in determining whether you're going to go with landfills or some other method, and access to the landfills, right? So the question really is, how can such operations be analyzed objectively? How can you create these models that allow you to change, toggle and kind of, change these variables and see what the effect might be on the end result? And where in this entire process can we identify financial and productivity incentives for recycling? So if you want to incentivize recycling, it would best serve everyone, and especially if you can work with the contractor to see where in their process does it make sense for them to do recycling rather than go with another, rather than just going to the landfill straight away. And how can we get really into the nuts and bolts and make some tactical decisions about how much equipment do we need? What is the impact of having this equipment at this location in preparation for a disaster? So these are some of the questions that we can get to answering with discrete event simulation. So at this point, I'd like to introduce this discrete event simulation software. I don't know if any of you have heard about this in the past, but essentially it is a modeling tool for analyzing operations. And operations and processes, they're kind of used a little interchangeably. But essentially what you do is you create a workflow or a flowchart of the process. You specify what resources are there and what logistical constraints there are, and it'll analyze those operations for you, as we'll see. So particularly discrete event simulation is good when you have a lot of resource interdependencies. So going back and thinking about our debris problem, right? We have wheel loaders and excavators that load debris onto trucks. So you already see that there's some resource interplay happening there. And then trucks take this to the temporary debris management sites. And the temporary debris management sites, they can accept the debris only if it has room for processing the debris. So there's a little bit of a local constraint there, right? And how do you determine if this site has space? It's based on the operations that happen after the site. So the debris has to be processed and taken to the next step of the process, which might be final disposal or taken to a recycling yard or something, right? So you can start to see how all these geographically dispersed logistical constraints start to have an impact on your operational productivity. So discrete event simulation gives you a means of objectively trying to quantify those things. We'll walk through those. And the outputs that you get are typically insights into metrics like time, your time and cost of operations, the what fleet configuration you might have based on what operation characteristics you have, and what are some of the other bottlenecks that might arise in your entire workflow that you've defined for your operation. All right. And just getting in a little more technical into what how to do discrete event simulation. So in the software that I'm about to show you, discrete event simulation models are described in terms of what we call activity cycle diagrams. And they are network diagrams which where you have nodes and links. And your nodes can basically be of three types. You can have queues, combis, or normals. These are kind of grouped together as activities and forks. And you have links to connect these nodes. All right. Here's just a quick description of all of these things. So queues are essentially nodes that resources wait when they're idle, right? So you can think about an excavator or wheel loader waiting for a truck to arrive. It's going to be sitting in a queue. Whereas activities are actually things happening. So these are steps in the process that you expect, that you want to study, right? They have a duration to them. And maybe the excavator loading a truck with debris is one example of an activity, right? And hauling the dirt, hauling the debris to the disposal or the debris management site is another activity, okay? And you have forks, which are used for probabilistic routing of resources. So sometimes you have a choice of whether you want to go one way or the other in your operation based on whether you have wood debris, vegetative debris versus demolition debris. So you can kind of start to create these branches in your operation based on certain characteristics. So what we're going to do now is we're going to actually start to model a very simple operation. I'd like to kind of talk you through this process. All right. We're going to do a simple operation where we are going to model a debris clearance operation where a wheel loader loads debris onto trucks, and these trucks take the debris to a dump yard, to a debris management site where it's processed. All right. So I hope there are no questions about what operation we're doing. It's basically a very simple load, haul, dump, return operation. So you see that the wheel loader might load debris into these trucks. The trucks take it to the yard. Forget this dozer here. We're not going to work with that yet. And then these trucks come back and get loaded again. So this is how these operations happen, right? So some questions that might be of interest for an emergency manager or for a contractor might be, based on the local site conditions, how many trucks do I need if the trucks have a capacity of 20 cubic yards? How much space is required at the dump zone to prevent the overflow of trucks? So these are all very tactical decisions, right? If you can think about it, we're trying to take into account the space constraints, the capacity constraints, and the types of resources that we have and working on it. So before we start getting into JSTrobe, I just ask you to think, okay, about what are the main activities that we can identify from this simple operation, right? So maybe you can put it into chat. Let's make this a little interactive so you're not just listening to me. So in chat, just type down what activities are going to be involved, what major activities are going to be involved in this operation of moving debris from one place to another. I'll get you started. So we have the loading activity, right? So the trucks need to load debris onto the excavator. Yep, loading. What happens after the truck is loaded? Transporting, thank you, Hayan. Moving of the trucks, exactly. What happens after the truck reaches the dump zone? Dumping, there you go. And after dumping, it just comes back, So we've identified like maybe 4 activities, right? Load, haul, dump, and return. And now what we would like to think about is what conditions are needed for this activity to start, right? So think about it. So what conditions need to be met in the operation for loading to start? So Jian, you asked a great question. Do we need to think about getting labor? We're just assuming for this simple example that the labor is already available, okay? But thanks for that question. I'm just responding to something in chat. So let's think about this. So for the load activity to happen, we need to make sure that the wheel loader is idle. It's not loading up another truck, right? We also need to make sure that there's an empty truck that's available to be loaded. And we also need to make sure that there's enough soil or debris, as the case may be, in the stockpile, right? And the outcome of the load activity is, after the load activity happens, the wheel loader goes back to waiting for the next truck. The truck gets ready to haul, and that's it. And the debris pile reduces by a little amount, right? So you can start to think through this for all of your conditions. For haul, all we need is a loaded truck ready to haul. And at the end of it, you have a truck that's ready to dump. So that's how you can think about these operations. And what we're doing here, if you think about it, is we're discretizing the operation into 4 different activities. Okay, that's where the name discrete event simulation comes. So we've broken down this operation into smaller chunks that we can measure, we can get some metrics for, we can get some conditions to get started for, and so on. So at this point, I'm just going to switch over into the JSTrobe software. So I know Hiba and Juyang have shared this software with you. Hopefully you are able to install it. And it's, as you can see, there's not a whole lot of things to learn about the software, but I hope that once you learn this, you can start to analyze a whole broad range of different operations. All right. So what I'm going to do is I'm just going to start creating this operation. So let's just start to do that. All right. Now, if you recall, for the load activity, I'm going to use one of these combis. And I'm using a combi because multiple conditions need to be met for the load activity. Let's assume that this takes about, let's assume this takes 5 minutes. I'm just going to put a number 5 here, right? So this is the time that it takes to load a truck is 5 minutes. That's all it means. Now, what do I need for the load to happen? I need debris in the pile. How much debris do I have? Let's assume that Hazes tells me that I have, I'm going to say 50,000 cubic yards of debris. That seems like a pretty good amount, right? So we have 50,000 cubic yards of debris that we want to move, right? So I'm going to keep this here. And you see that I've put it in a queue, right? Because that's a resource that is participating in our operation. And each time I load a truck, I'm going to remove 20 cubic yards of debris from the truck. So I'm going to just specify this. So I'm going to use this. You see this drop-down menu. I'm going to get a logical operator from there that says that as long as I have more than 20 cubic yards of debris in this queue, I'm going to keep removing 20 cubic yards for the load activity. That's all this means. All right. Apart from this, I have the wheel loader, right? So I'm going to have a queue for the wheel loader. And let's say I just have one wheel loader, right? It's the same thing. All I need for the load activity to start is I just need one wheel loader in this queue to start. So this condition works fine. It says that as long as the number here in this queue is greater than 0, I can start this activity, and I'm going to take out one wheel loader from here for this activity. And finally, I have trucks, right? Trucks. I'll just call it truck. And let's say I start with 6 trucks. So do y'all, I mean, I'll just pause at this point to see if anyone has any question about any of this stuff that I've done. And I'm going to also start to think about what happens after the load activity. Okay. So feel free to just step in and add in chat if you have any questions. Hopefully you're with me at this point. Now, what happens after load? So after load, the wheel loader returns to the wheel loader queue. And that's what we meant by saying that, after the load activity happens, the wheel loader is just waiting for the next load activity to happen. Right? And after load, we can have the haul activity to happen. And let's just assume that it's going to take us anywhere between 20 to 30 minutes to get to the dump site, right? And that's what I mean by uniform 20 to 30. And this really allows us to not consider, we can have stochastic values, so we can have some probabilistic distributions, which makes it a little more accurate. And really, when you start to study these queuing systems, you find that queues accumulate not because there's too many customers, but because of the uncertainty of their arrivals. That's why you start to see queues. So it's important to have this capability for our analysis. And our truck will start to haul, right? And after it hauls, we said it's going to dump. Let's say it unloads or dumps. Let's say that takes about 3 minutes. And we have I'm going to call this the dump pile, okay? Just because I can't think of anything else. And after we dump, we're dumping 20 cubic yards of debris into the dump pile, right? Because our trucks are that, we're taking 20 here and we're transporting that to this point here. That's what we've been doing. And finally, we have our return activity, and let's just assume that that takes a little less than hauling. So it takes about 17 to 25 minutes on average. So our truck dumps the debris into this dump pile, and then it returns using the return activity. And when it returns, it joins the queue again for trucks. So this is a very simple example, So let's start to see how we might run this. I'm just going to, so if you see there's some features for zooming in and out, and there's a feature for animating this operation. So I'm just going to change this and just start to show you what this looks like. So when I hit play, you start to see that I've the load activity can happen, and you see how the load activity ends at time 5. The truck starts to haul and the second load activity happens, right? I hope that's clear to you, So green means that an activity is starting and red means that an activity is ending. So what we're seeing here is trucks are getting loaded, and all these other trucks that have been previously loaded are still hauling. All right. None of them have reached the dump yard yet, because I know that because I can start to track them. So I'm just going to increase the speed a little so we can rush. We can move faster. So you see dumping is happening, and you start to see that the debris is being reduced from this pile and it's being added to this pile, right? And then the trucks are coming back, and you see that there's no load happening because there were no trucks, but now it's going to start happening again. And we can just kind of move fast, and you start to see this thing start to accumulate, right? Of course, we're not going to stay for the whole thing. So I'm just going to turn off animate. It'll take a couple of seconds and the simulation stops once all the debris has been moved from this pile to this pile. Okay. I see. Oh, that's a great question, Mohammed. I'll get to you in just a second about that question. Okay, 1 second. So when I look at the results, right, what am I interested in the results? So the first thing that I might be interested in is how much time does a total operation take? So in this case, it takes us about 23,000 minutes, okay, which you can convert to hours and you can build in your breaks and so on. But it gives you this number here, gives you an idea of how much time the entire operation takes. We also care about things like how long does the truck have to wait for the excavator. So we're doing pretty good here. You know, you see that we're only waiting. We're waiting for about each truck on average waits about 119 minutes, 1.19 minutes when they come to get loaded by the excavator, which is not too bad because considering that the load activity itself is 5 minutes. But we see that the wheel loader is kind of idle, right? It's waiting a lot of time. It's waiting for almost 50% of, you know, it waits for as long as it takes to load a truck. So we probably want to consider maybe increasing the number of trucks in this situation. Let's try to do that and we'll get back to just analyzing the operation. So instead of 6 trucks, what if I had 8 trucks? Okay. Now I'm going to run the entire thing with 8 trucks. I'm turning off my animate. I'll take a couple of seconds. Yeah, your simulation's ended. Yeah, you see, so we've gone down from 23,000 to about 17,000, right? And as you might expect, the more trucks we add, the more our average weight is going to be for the trucks, right? It's just like, you know, if you have more customers at a bank, the average weight per customer goes up. So we start to see those as real numbers. And we also start to see, okay, what is the wheel loader? The wheel loader's wait time has come down from, what is it, 4.19 to 1.95. So we're kind of doing better in our operation overall, I would say, right? Now, Mohammed has asked an interesting question in the chat as to what is the difference between a combi and a normal, right? So just to kind of refresh your memory, combis have this, they look different because they have this little clipped edge. They have a clipped edge, whereas normals are fully rectangular. And the only difference is that for combis, you need multiple conditions to be met, okay? Whereas queues represent activities that can happen right after the previous combi is done, has finished up. That is the difference. So for instance, once a truck is loaded, the truck does not need to wait for anything else. It can just proceed to the next activity and it can start going on. Now, I'd just like to increase the complexity of this model just to start showing you how we can model different logistical constraints into this operation, right? So this is a pretty simple operation, but what if there were some space constraints at the dump site, right? What if only 3 trucks, or let's say, what if only 2 trucks could dump at a single time? So we want to make sure that trucks don't just go and dump. We want to control the amount of trucks that are dumping at a single point of time, okay? So in that point, what I do is I add a little bit of a constraint. I model this as a token. So I'll call it dump token. Okay, I hope that makes sense. And I have 2 dump tokens so that only 2 trucks can dump at a time. And now all of a sudden we're introducing this constraint here. So I can no longer use a normal. I have to get rid of this one and just change it into a combi. Okay. And because of that, and this is something that you should also know, is that only queues can connect to combis. So I'll have to have another queue here. So that's just another trick in case you're wondering why. So we can have, because what happens is as trucks come to dump, they start to see that, oh, I need a token, so I might have to wait in line. So that's why you need a queue before you can get to a combi. So that's just a little modeling rule that you need to be aware of, all right? So we have a truck queue here for dumping. And initially you don't have anything in that queue, that's good. And then we can start to just reconnect these things. So what I'm doing here is I'm using a token system to control the amount of trucks that can dump at a single point of time. Okay, I hope that's that's clear to you all. And as soon as, let me rename this as dump, and it takes 3 minutes to dump as usual, right? As soon as I finish dumping, I return the token. So the next truck can dump as long as, there are trucks in this queue. So let's see what this does to our operation statistics, right? I'm going to run this again. Let's look at it. So this did not make too much of a big difference because we still have about 17,000. And the number is going to change every time just because you have some stochasticity that's built into your model, right? Let's see if we can make this. Let's say I have only one truck dumping at a time. Let's see if that makes any difference. Still no difference. So I guess this is not a big bottleneck. So what's happening here, what you might imagine as to happening here is that trucks are arriving at a rather large, they have a rather large gap between them arriving. The other thing to think about is that because this dump takes only 3 minutes, it's not too much of a queue building up. But let's change this, let's say to, I'm going to change this to about 10 minutes, So it takes, let's say it takes 10 minutes for the trucks to go in, to maneuver to the correct dump spot, to get the ticketing done, and then move out. And they have only one token. Let's see if that makes a difference. Yeah, now it makes a huge difference, right? You see that we've gone up from 17,000 to about 25,000, right? And how much of that was due to the token? Let's see. So let's change this token to, let's say we have space for 3 trucks. So you see that there's a significant difference. It was 25,000. All of a sudden, you start to see that there are trucks accumulating in the truck queue. Okay. So if you look at this truck queue, we start to see that there's slight weight here because it's 3. But when we change it to 1 again, let's see what the weight is. You can start to see the big difference, right? You start to see that trucks are waiting for 18 minutes at this queue because they're waiting for the trucks in front of them to dump. So now you can start to see how different physical constraints in your local, in the area that you're studying or that you're modeling for can be translated into these types of discrete event simulation models. Okay. Now, other things that you can also think about, for instance, are, let's say the dump pile. So the TDMS capacity is limited to 1,000, right? So you can have a little condition in here that says it's less than or equal to 1,000. Only then can I dump. So I'm not drawing anything because I'm just checking. But what we're saying here is I can only dump into this dump pile if I have if the amount that's in there is less than 1,000 cubic yards of debris. So you see what's happening, right? So what we're seeing here is we can start to build up the complexity of our models just using these simple rules that can be defined as in these logical constraints, okay? And what you would also typically do in such a case is you'll have to transport, I'll just say take to landfill, right? And that's going to maybe take you 20 minutes or let's say 40 minutes. So in this case, we want to also ensure that we have another set of trucks that are taking our debris from the dump pile in the TDMS site to the landfill. So you can start to build out your model this way, and you can start to get some very complex models, and you can start to see how all the decision points that we talked about earlier have some role to play in this operation, and they can affect the operation in some manner, right? So I'm just going to do this, and we need trucks for this. So I'm being very simplistic here, and I'm going to have another type of truck. Let's say I have 10 trucks that are constantly doing this thing. And all of a sudden, you can start to see that you're going to start to have multiple sorry, give me 1 second. I'm just going to make this greater than or equal to 20 and remove 20. You're going to start to have multiple bottlenecks in this operation as we start to like build it out. And this gives people of different experiences and different backgrounds a way of looking at the operation as a flowchart. You know, it's not ideal, and we'll see some methods in which it can be, we can better express these flowcharts, but someone who's building it can take into account all of the logistical constraints that they have for their operation. So I'll just run this once and then we can kind of get back because I'm already running out of time, I think. So all of a sudden you start to see that, you know, we've gone back up to 25,000 minutes for our time, and we start to see some huge average weights. You start to see that the truck 2 has a lot of weight because it's waiting for the debris to build up here before it can move. You can start to see that the truck queue, or this queue, has some weights. So you start to see how these bottlenecks, because you added one new element to the operation, starts to propagate throughout your operation, right? So because we're already at 140, I'd like to quickly switch back to our presentation and just talk about how this integrates with the larger goals of debris management. All right. So let me switch here. There we go. So we've done the demonstration, and I would encourage you to just, you know, I've given you the handout, and that kind of gets you started with playing around with these models, right? So try to start thinking about playing around with some simple models and start to build up the complexity as you start to add more stages of the operation to your model for analysis. And these are the questions we can analyze. How long does it take to clear all the debris that you have in your operation? How efficiently am I using my resources? That is, are my trucks waiting too long in queues? Are they stuck in queues? And so as you start to get economics involved in this, right? You can start to cost out and price out your operation and start to think about, okay, where might recycling be an option as opposed to taking it to the landfill? Just moving forward, here's another visualization of these types of operations that can be generated using the models that we just saw, okay? So this is kind of useful to communicate these types of models to contractors or to folks who may not be as familiar using the modeling tools themselves, but anyone can understand this visualization. So here's just an example of a quick discrete event simulation model that visualizes 2 excavators working with a fleet of trucks. And you also have the added complexity of having a one-way curve in the middle, right? You start to get really useful metrics like your production metrics, your utilization metrics for your excavators and shovels and so on. And you can also, in the next slide, you can start to see how you can brainstorm ideas to see how you can remove bottlenecks. And you can do all of this in the simulated environment, in a virtual setting, rather than in a, you know, you don't have to like actually do the operation to kind of start trying out these methods. All right. So quickly, I'd just like to talk next about how these can be integrated all together with tools that we're familiar with. So we've spoken about debris forecasting, right? And for these, they take in inputs like disaster type and study area and the disaster magnitude, and tools like HAZUS from FEMA, EPA's iWaste tool. They can provide information on the quantity of waste that's generated. They can quantify the loss that's going to be experienced by a community. And we can do various types of geospatial analysis to both identify suitable locations for temporary debris management sites, as well as routes that need to be taken from the debris locations to the temporary debris management sites and further to the landfills or to the backfills that you have. And discrete event simulation really can take information from both of these. So you saw how we used debris quantities earlier and how we used haul durations, right? So all of that information really comes from doing a geospatial analysis of your study zone and a debris forecasting analysis of your study area or your community that you're looking at. And in discrete event simulation, you can start to have various disposal strategies that you try out by just building out these models for various strategies. And you can start to think about which strategy gives you the lowest recovery time and the lowest removal costs for your debris. All right. So we're at 1:45 now. I'd just like to pause to see if we have any questions. Well, I'm hearing none. So what I'll do is I'm just going to go on for another 5 minutes, just quickly show you how I implemented this methodology for a case study here in Oregon. Okay. So what we did was we looked at FEMA's guide for how you can dispose of vegetative and construction and demolition debris, and saw what steps are available, what steps are needed to go through these two types of debris, right? So the first step was to forecast the amounts of debris that were generated, and we did this for two coastal towns in Oregon called Astoria and Newport. And what we got was, we got to see the debris forecast in tons and this is for Astoria. You can see we got both the amount of debris and the distribution of debris. And we determined that the total amount of debris is about 200,000 tons for a 9.0 magnitude event. The next step was to do some geospatial analysis to identify suitable temporary debris management sites. So this is very important for us, our local situation, because when you think about these coastal communities, they are really cut off from, the inland communities where you have all the landfills, right? So it's important for them to have these temporary debris management sites where they can process and reduce the debris before it's shipped off either to landfills or for use in recycling applications and so on. So what we did was we were able to create a tool in ArcGIS to help us identify potential sites for debris management sites. And what you see here is all we've done is we've taken the recommendations from the EPA that the site cannot be housed near residential communities or schools or hospitals or any of these critical facilities, nor can they be near environmentally sensitive areas. So it gives us potential sites. And then we were able to identify the shortest path to go from one location to another after a disaster. And this itself is a very interesting area of study, I think, because we're really getting in some structural analysis to identify which bridges and which roads are in a serviceable condition, can provide service after a disaster. So this allows us to identify the shortest access routes. And just a quick illustration of this is, this is for another coastal town in Oregon. You see that this is the shortest route between this fire station to electrical facilities in peacetime, or even during an 8.1 magnitude earthquake. But we see that the route changes considerably. So there's an increase of, I think, about 5 miles. And you can imagine what that does to your cycle times, right? Because this bridge was found to have sustained some damage, which prevents the passage of trucks through it. So bringing together all of this, you can start to create your models. And what I've just shown here is I've just represented how the physical constraints are represented in the models. So all it takes is just one link from a queue or a combi to kind of prevent the start of that combi unless it meets some kind of a logistical constraint. All right. And what we did next was we started to map out the entire process for vegetative debris operations. So you can start to see here that we add the TDMS, we dump it, we segregate the vegetation either as waste or as wood that can either be grinded or incinerated and eventually taken to a landfill or recycling. Now these guides are great, and this is what FEMA gives us, but they do not provide us with any type of quantitative measure by which we can assess their impact or assess recovery times and so on. And that is where something like this JSTrobe discrete event simulation software that's what will help you do, right? So we were able to essentially map this into a model for further analysis. The same thing was done for construction and demolition debris. There's plenty of guidelines out there that tell you what to do with the debris. What we've done with what we are able to do with this tool is just to take that a step further and start to quantify the measures there. And that really starts to tell you, based on your available resources and your local situation, we can start to get to identifying bottlenecks and so on. All right. So this is what we did here. And I'll just skip to get to the questions. But I just want to show you this slide eventually what we can do is we can help decision makers think about where they might be able to stage equipment and how much equipment they might need to get to meet their resilience targets, essentially. All right. And because it's SUMMEER and there's an emphasis on data collection, I'd just like to encourage you to think about what data might be useful for analyzing operations and analyzing processes, right? So you'll need to know things like what are the activity durations for various types of debris. That is not something that's easily known because most of the equipment that we use is created or designed to work with more homogeneous material and not demolition material or the form of that debris takes. So that's something that's worthwhile. You also need to think about how long does it take to sort debris. These are all very useful metrics that would really guide decision making if we were to move forward. All right. I also wanted to show you this page. So JSTrobe is a software that I've created. It's available for free at this website. Okay. And but it's based on a software called Stroboscope that was developed by my advisor earlier. It's an amazing software. The only disadvantage is that it requires this Microsoft Visio to run. But you also have more robust commercial software like AnyLogic, and it should say Arena here. But these are commercial softwares that I'd also encourage you to check out. Of course, that requires a fee. And this also answers one of the questions that is asked by Anisha, which is how do we convert the flowchart to visualization? So we can do it either using commercially available software, or we can do it by instrumenting this discrete event simulation to generate animation instructions that can then be read by something like Unity or Vidascope to generate these operations. And I would be happy to provide those resources. If you just send me an email, we can get into some more of those details here. So Piyush asked a question about the use of a fork in the simulation tool. So we didn't really use fork here, but let me just go back to one slide here that shows that. So you see here, right, Piyush, we have vegetative debris that could, when you segregate it, you can either get waste material or you can get vegetative wood and debris for processing. So that is one type of a situation where we might use a fork. So based on the material that's coming in, there's some kind of a probability assigned to whether it's going to be waste or whether it's going to be vegetative and wood material, right? And Jian, you have a question about contractors using potential sites in the future. Could you just clarify the question in chat, Jian? And I think Nazli has a question, so let's go to Nazli in the meantime. Nazli, if you could please unmute yourself.
Yes, doing it a bit slowly, but thank you for the nice presentation, Joe. And my question relates to, I think perhaps you answered this in some fashion, but when you are trying to deal with operations that have to happen sequentially, and there are big time gaps, let's say, between the different components, probably can handle it by assigning limits on the amount that can be handled at a time, but can you put time limits also, meaning you have to do the TDMS for maybe several days and then move to the landfill operation afterwards? How do you handle those potential gaps between the different components?
Yeah, thank you, Nazli. That's a great question, and there are two ways in which we can do that. Either that time gap is a result of resource availability or activity duration. So for instance, let's just assume that this is TDMS processing, I'll just say that. We can change the time to as long as it needs to be. So we can say that, it's going to take 8 hours to process a certain amount of debris. That is one way of doing it. And the other way would be to artificially inject some kind of a gap between events. So for instance, what we can say is we can assume that let's just assume we want to insert an artificial gap. All you would do is, just insert this normal in between two other activities that will happen. That might be one way of doing it, right? And you can also have things like inserting the forks into activities. So for instance, we might have certain situations where it's very easy to handle the debris, whereas 10% of the time, it might take a longer time to handle it, right? So forks might be another way of trying to model those specific situations.
Yes.
But
Okay.
thank you, Nazli. Hope that
Thank you.
answers the question.
Yes, thank you.
All right, and do we have any other questions? Well, thank you all so much for the questions, and I'm sorry I had to rush through the last part of it. But essentially, the important slides I would like you to think about are the resources on what you can do moving forward, which is what types of software are available to help you do the discrete event simulation. There's JSTrobe, which you already have, hopefully, and there's more sophisticated tools that might also integrate visualization with the modeling. All right. So at this point, Juyang, maybe I'll give you the floor.
Yeah, thank you so much, Joe. I know you have a lot of things you may want to talk about JSTrobe, but thank you so much to amazingly, summarizing the JSTrobe within the 45-minute time constraint. And I think one of the audience has a questions and which needs a little bit more clarification. So Jianyun Shan, do you want to speak to Joseph and clarify your questions? Probably Hiba, can you please allow him to unmute himself?
Yeah, hi. My question was really just, I think you mentioned in your slides that you identified a bunch of sites based on the EPA's regulations and things like that. So I'm wondering, are those existing sites or the sites that based on the research or the geospatial analysis will be recommended in the future scenarios?
Yeah, that's a great question, Jayan. So I'm just going to get to that site really quickly. It's before this. Yeah. So so for the geospatial analysis, right? I think it's just something, just because of the variety of sites that we would, a variety of considerations that might be required to choose a site, we cannot do all of it automatically. And all that this GIS analysis does is it cordons off areas where you should not be thinking of putting sites for your TDMS. Okay. So for instance, these red areas, you can see that they're the areas that are near to the coast, and so they are environmentally sensitive. And there could be some, maybe depending on the local context, there are wetlands, there's hospitals or schools located close by. The sites that are typically chosen are flat areas, if they've not identified it previously, which can handle the ingress and egress of trucks, as well as flat open areas for processing the debris. So that would have to be done more manually, I would say. But thanks for clarifying your question, Jian. Hope that answers it.
Okay, I know we are almost out of time.